Welcome back to G Fun Facts Online. Today we are stripping away the crust of our planet and descending into the deep, dark, and crushing interior of the Earth to solve a mystery that technically should not exist. We are talking about deep earthquakes. These are tremors that originate hundreds of kilometers beneath our feet, in a realm where the laws of physics, as we usually understand them, tell us that rock should flow like honey, not snap like a twig. Yet, against all odds, the Earth is snapping. To understand the magnitude of this paradox, we need to travel back to May 24, 2013. On that day, beneath the icy waters of the Sea of Okhotsk, off the coast of Russia, a monster woke up. It was a magnitude 8.3 earthquake. To give you a sense of scale, that released energy equivalent to 35 megatons of TNT. If this had happened near the surface, it would have devastated cities. But this leviathan stirred almost silently. It generated gentle rolling waves that were felt as far away as Moscow and Tokyo, but it caused no damage on the surface. The reason? It originated from a depth of 609 kilometers, or 378 miles down. This event, the largest deep-focus earthquake ever recorded, reignited a scientific debate that has been simmering for a century. Because according to standard rock mechanics, what happened in the Sea of Okhotsk is impossible. Let's break down why. At 600 kilometers down, you are deep inside the Earth's mantle. The pressure is so crushing that the atoms within rocks are squeezed tight. Simultaneously, the temperature soars above 500 degrees Celsius, or 700 degrees Fahrenheit. In these conditions, rock behaves plastically. It becomes ductile. Imagine a bar of chocolate left out in the hot sun. If you try to snap it, it just bends, stretches, and flows. It doesn't crack. That is how mantle rock should behave. It should flow like taffy. For an earthquake to happen, you need brittle fracture. You need rock to act like a cold ceramic plate that stores stress until it snaps violently. So how can rock at 500 degrees Celsius, under millions of atmospheres of pressure, snap like a dry twig? That is the paradox of deep earthquakes. They are the ghosts of the underworld, and today we are going to explore the 3 leading theories on how they happen, and look at the specific case files, including a major scientific update from 2025 that changed our understanding of the deepest quake ever recorded. But first, we need to understand how we even know these things exist. In the early days of seismology, scientists believed the Earth's interior was a silent, flowing conveyor belt. They thought earthquakes were strictly a surface phenomenon, limited to the top 50 kilometers of cold crust. But in the 1920s, a Japanese seismologist named Kiyo Wadati began noticing anomalies in his data. While most earthquakes in Japan struck shallowly near the coast, his instruments picked up seismic waves arriving from a source much farther down, hundreds of kilometers beneath the surface. Around the same time, American seismologist Hugo Benioff observed a similar pattern. When they plotted the 3D points of origin, or hypocenters, of earthquakes near ocean trenches, they saw a clear pattern. The earthquakes didn't just happen at the surface. They traced a diagonal line, a dipping path descending deep into the mantle. They had discovered subduction zones. These are the colossal collision sites, where cold oceanic plates crash into continental plates and dive, or subduct, into the Earth's interior. Those dipping bands of seismicity are now famously called Wadati-Benioff zones. They proved that solid slabs of the lithosphere, the rigid outer shell of the Earth, were penetrating deep into the mantle. But proving the slabs were there was one thing. Explaining how they could generate shock waves at 600 kilometers depth was entirely another. Today, scientists define deep-focus earthquakes as those occurring between 300 and 700 kilometers down. Below 700 kilometers, all seismicity abruptly stops. The Earth falls silent. So, what is happening in that zone between 300 and 700 kilometers? After decades of research, mineral physicists and seismologists have narrowed it down to 3 primary suspects. We call them the Big Three: dehydration embrittlement, transformational faulting, and thermal runaway. It is highly likely that the reality is a complex interplay of all three, so let's break them down. The first suspect is dehydration embrittlement. This is essentially the theory of the wet earthquake. When an oceanic plate subducts, it isn't just dry rock. It acts like a giant waterlogged sponge. It carries hydrated minerals down with it. These are rocks like serpentine that have water molecules locked inside their actual crystal structure. As the slab descends, the heat and pressure force these minerals to become unstable. They essentially start to sweat. They release that locked-up water. This released water becomes trapped in the rock's microscopic pores. In the high-pressure vise of the mantle, this trapped water exerts an outward pressure. It pushes back against the clamping force of the surrounding rock. This is called pore pressure. It effectively counteracts the immense friction holding the rock together, momentarily allowing the rock to become brittle again and slip. This mechanism explains intermediate depth earthquakes, those between 70 and 300 kilometers, brilliantly. It fits the data perfectly. However, there is a problem. At depths greater than 400 kilometers, the heat is so intense that most rocks should have already thoroughly dehydrated. The sponge should be dry. So for the deepest monsters, like the one in the Sea of Okhotsk, we need a different explanation. This brings us to suspect number 2, transformational faulting. This is the most exotic and currently the favored theory for the deepest events. It involves an identity crisis of a mineral called olivine. Olivine is the primary green mineral that makes up the Earth's upper mantle. It is stable near the surface, but as it is dragged down below 410 kilometers, the pressure becomes too great for its crystal structure to hold up. It wants to collapse into a denser, more compact form called wadsleyite, and deeper still into ringwoodite. Usually this change happens gradually, but inside a cold, fast-sinking tectonic slab, the core of the slab remains too chilly for the atoms to rearrange quickly. The olivine becomes what we call metastable. It is under immense pressure to change, but it is stuck in its old form. It is like a compressed spring waiting to release. Suddenly, a nucleation point triggers the change. The olivine crystals instantly collapse into the denser structure. This collapse shrinks the rock's volume rapidly. This rapid shrinkage creates a vacuum-like anticrack, or a zone of weakness. The surrounding rock crashes inward to fill the void, generating a shear failure that mimics a fault slip. This theory neatly explains why deep earthquakes stop at roughly 700 kilometers. At that depth, the mineral structure changes again into bridgmanite and ferropericlase, and the metastable olivine fuel simply runs out. But there is a catch. For the absolute largest deep earthquakes, simple mineral collapse might not be enough to explain the massive energy release. We need something more explosive. Enter suspect number 3, thermal runaway. This is the theory of the self-feeding fire. Imagine a tiny slip occurs in the slab, perhaps triggered by that dehydration or phase change we just discussed. This slip generates friction. Friction generates heat. Now, rock at this depth is a terrible conductor of heat, so that thermal energy gets trapped right in the slipping zone. This trapped heat softens the rock further, making it slippery. This causes faster slipping. Faster slipping generates more heat. More heat causes more slipping. It is a catastrophic feedback loop. In a fraction of a second, a microscopic slip can escalate into a meltdown, allowing a rupture to unzip at supersonic speeds through the slab. This is the likely culprit for the supercharged deep earthquakes that reach magnitudes of 7.0 or 8.0. To see these mechanisms in action, we have to look at the specific case files, the crime scenes of the deep earth. Let's go back to the king of the deep, the Sea of Okhotsk event in 2013. Seismic analysis revealed that the rupture speed was incredibly fast, about 4 kilometers per second. The sheer size of the fault slip was over 180 kilometers long. This suggests a thermal runaway process. A small trigger lit the match, and the immense stress in the slab fueled a runaway thermal slide. It proved that deep slabs retain massive amounts of stored elastic strain, like a coiled spring waiting to snap. Then we have the anomaly, the Bonin Islands earthquake of 2015. This was a magnitude 7.9 event that occurred roughly 680 kilometers down. It was felt in every single Japanese prefecture, which hadn't happened since 1884. But the real controversy came from an aftershock in this sequence. For nearly a decade, scientists debated data that suggested an aftershock occurred at 751 kilometers depth. This was huge news because 751 kilometers is well into the lower mantle, where earthquakes should be absolutely impossible. It was hailed as the deepest earthquake ever. However, science is a process of correction. Recent cutting-edge reanalysis in 2025 has effectively debunked that 751-kilometer claim. The new consensus relocates the aftershocks to a shallower depth, though still an extreme one. The leading theory for the Bonin event is now the metastable olivine wedge. The Pacific plate in this region is subducting so steeply and so quickly that a tongue of cold, unaltered olivine has penetrated unusually deep, delaying its phase transition until the last possible second. The 2015 quake was likely the violent death rattle of this mineral wedge finally collapsing under the pressure. Finally, we have a very recent breakthrough from 2024, the Calama earthquake in Chile. This was a magnitude 7.4 event at an intermediate depth of roughly 120 kilometers. While shallower than the deep events, it acted as a Rosetta Stone for linking our theories. Researchers found that the quake started in a cold wet zone, pointing to dehydration embrittlement, but then ruptured violently into a hotter dry zone, where only thermal runaway could explain the propagation. It showed us that these mechanisms are not mutually exclusive. A water trigger can ignite a thermal fire. So why does this matter? Why should we care about earthquakes that happen 600 kilometers down, often too deep to cause damage? First, they act as an X-ray of the planet. Deep earthquakes are like flashbulbs in a dark room. The seismic waves they generate travel through the core and mantle to reach sensors on the other side of the world. By analyzing how these waves speed up or slow down, seismologists can create tomographic maps of the Earth's innards. They have revealed stagnant slabs of crust piling up at the transition zone like a logjam in a river. Second, they teach us about the water cycle. The existence of these quakes proves that water is being dragged deep into the mantle. If dehydration embrittlement is active at 300 or 400 kilometers, it means the Earth is swallowing oceans over geologic time. This deep Earth water cycle regulates the planet's long-term habitability and volcanic activity. And finally, hazard prediction. While usually safe, deep earthquakes are felt over much wider areas than shallow ones. The Okhotsk quake was felt 7,000 kilometers away. As our infrastructure, our skyscrapers and long bridges, becomes more sensitive to long-period resonance, understanding the unique ringing of deep quakes becomes crucial for global engineering safety. In conclusion, the mystery of deep earthquakes is a testament to the dynamic, living nature of our planet. Even in the crushing dark of the mantle, where rock should be dead and flowing, there is violence, change, and transformation. As we deploy denser sensor arrays on the ocean floor and develop better mineral physics models, we are slowly shedding light on these deep tremors. They tell us that the ground beneath our feet is not just a static platform, but a churning engine recycling the crust, hiding oceans in crystal lattices, and snapping under stresses we can barely comprehend. The next time you see a news report of a deep earthquake, remember, it is a message from the center of the Earth, a reminder of the immense forces grinding away in the deep, dark heart of our world. Thank you for listening to G Fun Facts Online. Make sure to subscribe for more deep dives into the science of our universe.